well, we're glad to have you, Richard, and Yves too. Um, and I'm glad, Richard, that you are doing okay. Uh, Maybe I'll come to New Zealand and visit you.
Do. You're always welcome.
Oh,
Let me
thank
know
you.
and I'll organize something for you.
Okay. All right, thanks. Um, I'd love to, but that'll be like uh, my dream goal here.
Mm.
Okay, guess what? I'm actually going to introduce Yves. See, I was kind of
Okay. All
sort
right.
of
So
on top of things.
let me not share yet. So you can go
Y-
ahead and introduce.
Yeah, let me just give you a brief intro, Yves. Okay. Well, first of all, welcome to our Govys, and we have a small audience, but that's okay because we have Richard's here, Yves is here, Donna's here, I'm here, and we're going to record it and post it to the YouTube channel for people to take a look at it. So I'm going to go off script a little bit. I usually don't do, an official little bio, but Yves gave us one, and so I'm going to read it, and it's short. So Yves is a fellow research colleague here at the Census Bureau in the Research and Methodology Directorate. He completed his PhD at Carnegie Mellon University in 1988, and he joined the record linkage group headed by Bill Winkler here at Census. So Yves has a really historical viewpoint or knowledge, if you would, of record linkage and how that's been developed and used here at the Census Bureau. And he's also worked on problems involving missing data and classification in addition to his record linkage work. And he kind of gave us a little like practice overview of what he's going to talk about. And I think it's a bit of a different take on record linkage, and also not just like using the R package or Splink, but kind of how can you use R itself, and kind of doing the models yourself without using the packages. Although he'll clarify that. Anyway, we only have still, we have some other attendees. Great. And so those of you who are here, thank you. And also we have a Q&A feature and the chat feature. So just put your questions in there, and when it comes time for Q&A, we will ask Yves the questions. So Yves, I'm going to pass the podium to you for your talk. Thank you again for doing this.
Okay. Okay. So here. Okay. Thank you, Wendy. So thank you for the introduction. What I'm going to say is my professional opinion, and in no way is the official opinion of the Census Bureau, of the U.S. Census Bureau, or CSRM. Let me tell you a little bit about record linkage at the Census Bureau. The research group, uh, we are four colleagues, Emmanuel Ben David and Rebecca Stewart and Daniel Weinberg. There's a strong involvement and support from the Center of Optimization and Data Science. And there's also expertise in multiple areas, in the three main areas of the Census Bureau: the demographic, decennial, and economic area. Where I can't mention everybody, but there are seasoned experts in each of these areas who do record linkage. So this is only one part of what we do. I want to give special thanks to Serge Allison Gwendell, who looked over the early version of that presentation. So I'm going to introduce pairs and clusters, the concept of pairs and clusters that we're trying to link in record linkage, and discuss one-to-one link file and the statistical methodology in the process. I'm going to focus on two main pieces of work. One is the breakthrough of Mauricio Sadinle and Steve Fienberg, when they generalize the commonly used Fellegi-Sunter methodology, which is, you probably heard of, which is the mainstay in record linkage. Most packages out there are at least partly based on the Fellegi-Sunter methodology. And the other piece of work I'm going to pick on is the paper of Steve Fienberg and Alessandro Rinaldo, when they extended maximum likelihood estimation in the context of log linear model. I'm going to show how you can use these concepts to extend the Fellegi-Sunter type methodology, which has serious limitation, and it's what I'm going to discuss first in the paper. Now let's think about what record linkage is. We have clusters, and we are trying to assert a matching status for records in the cluster. They can be pairs, it can be triple, and for the sake of the argument, I'm going to think about records of persons, but they can be records of anything: businesses, entities, organizations, countries, whatever. And also I'm going to assume that you can compare the records in the cluster on agreement field, okay, on field agreement, on comparison field. And that's all that matters in this case for this presentation is the result of the comparison. For example, person record can be compared on the first name, on the last name, birth date, and so on. There's a lot more possibility, obviously, but all that matters is whether you have an agreement or not. And this is very simplified. Of course, record linkage can go beyond that and beyond just agreement or disagreement. Also, the content of the field could play a role, but we are not going to go there. Okay, so when you have pairs, you have only two possible matching statuses. Okay, we're going to look at an example, and the three comparison fields are going to be first name, last name, and year of birth. Simplify the situation. And so you have 8 possibilities: disagreement or agreement on either of those 3 fields. And there's an underlying matching status that you don't observe. Okay, this is a situation that I'm going to discuss here. Right? We have those files going to link, and we do not have training data. It can be extended to cases where you have training data and supervised learning and so on. That's very powerful, but I'm not going to talk about that. I'm going to talk about a classic situation that Fellegi-Sunter introduced in their paper in 1969. And the basic assumption is that the cluster are independent, and that is very important. So if you have pairs, comparing record A and record B is independent of comparing record C and record D, okay? And within the cluster, you have conditional independence. The agreement pattern follows is governed by a conditional independence rule. That is, if indeed the 2 records of the pair point to the same individual, you're going to observe agreement, disagreement on the first name, last name, and so on at random independently. There's no dependencies between the agreement fields, the comparison fields. And similarly for the non-matches. Okay, so that's the basic structure of the model that is still being used. It leads to additive scores, and there's all sort of computational nice things that come out of this, even though if sometime these assumptions are clearly violated. And we're going to discuss that a little bit. Okay, so for example, if you have only 2 files, And let's say each file has 2 records. So you have 4 possible pairs, right? And so each pair can act as either a match or a non-match. Sadinle and Fienberg introduced a partitioning in record linkage. I can't get too much into it. It would take me too much time. But basically, they came out with this notation, the set theoretical notation to identify the status through partitioning. So when you have pairs, very simple. There's only 2 possible partitions, non-match and match, as you can see here, expressed through this set theoretical notation. Okay? The independence assumption means that if you are going to match these 2 files, you're going to have one-to-one linkage. Okay? You cannot have one record that is linked to more than one other record in the file that you are matching against. Okay, that would violate the independence assumption. This situation is not one-to-one, as you can see. What you have there implicitly, there are duplicates in that file, and therefore there are other links that you don't see. And in effect, you no longer have a pair, you have a triple. And if you have a triple, you cannot have independent pairs. A triple cannot be constructed from independent pairs in general. That's fairly intuitive, right? If A and B match perfectly, agree perfectly, and A and C agree perfectly, well, automatically B and C agree perfectly. So there are dependencies. So the traditional Fellegi-Sunter methodology breaks down. So let's think about going beyond just pairs. Okay, let's think about linking tree files and then considering triple. It's the same story. We want our triples to be independent. We're just considering here the possibilities that you can have multiple pairs connected to kind of overlapping pairs, if you will, and ensuing triples. Okay, so you have going to have to characterize the status of each triple. Now there are 5 possible status or 5 possible partitions when you have a triple, right? You can have either the tree record in the triple can be standalone, they each point to a different individual, or 2 of the records in the triple point to the same individual, but the third one does not. And you have 3 ways of doing that. Or all 3 records point to the same individual. So you have 5 possible matching statuses. Here's an example of tree files, of linking tree file. And those links here, like the blue triple, okay, is independent of the pink triple, and then you have a double Lucy. So this linkage structure define a partition assignment. That is, these are the higher order structure, higher order cluster that define the linkage structure, and then you can deduce exactly what the partition for the other pairs are. But the entire partition assignment devolved from non-overlapping triples. Okay, so independence is being maintained, and of course you can go to quadruple and so on. It gets more and more complicated. The point is you cannot piece together independent pairs to get there. You have to consider all the possibilities. Okay, sort of an exhaustive enumeration of the sampling space, if you will. Okay, so you want to do that classification to estimate what the linkage structure is. What is often done, and then that's what's usually done with in the Fellegi-Sunter paradigm, is to treat the problem as a missing data problem, and use the EM algorithm. And effectively, we have a mixture of multinomial distribution here. I'm not going to get into the detail, but you can use the EM algorithm to maximize the probabilistic structure underlying the linkage structure. And so the EM algorithm it's been around, it was around for a while, but in 1977, Dempster, later Rubin formalized it. They crossed all the T's and the I's and provided a general proof of convergence. And it's been used in record linkage since the 80s. Winkler, Jarrow, and Winkler says that the first person who did it was Pat Kelly at the Census Bureau, some obscure government employee. Of course, that's always the case. But so I'm going to give an example here to show how this works. I mean, I constructed 3 files from the so-called RL 10,000 data register, which is a register of 10,000 records, 1,000 of which have exactly 1 duplicate. Those are records of German patients, so German names, and it's in the public domain. It's available from the record linkage package authored by Suriyar and Borg. So I created 3 files of 200 records each, and the underlying the truth. Of course, you don't observe the truth in reality, but this is a simulation. And so I constructed the files so that you have these underlying partitions here. Okay, each of the 3 files has 500 standalone records that don't match any of the record in the other files, and it has 50 records. Each of the 3 files has 50 records that are involved in pairwise matches, the 3 possible pairwise matches between file A and B, file A and C, and file B and C. And each file has 50 records that is involved in a triple, in a 3-way match, in a full match. What we observe is mirrors the underlying linkage structure, right? So we create this triple. We have 8 million possible triples. And what we can observe is whether or not the 3 records agree on the comparison field. And there's 5 possible configurations. You could have for each field, you could have no agreement at all, 3 separate first names, okay? Or the first name is the same for file A and file B, but not for file C. Similarly for AC and BC, or you have a full agreement on the first name. And it's the same for first name, last name, and year of birth. These are the 3, for the sake of the example. These are the 3 matching field I am looking at. And to construct the observed statistics, I'm going to piggyback on FastLink. Okay, we don't have our own frequency count, but so I'd be happy to make the code available. And here is the observed statistics. Okay, the number of triples, the number of triple in each configuration, the 8 million triples. So you have like over 6.5 million of them. That shows triples that involve record that don't agree on anything. The 3 fields come out as disagreement between the 3 possible pairwise comparisons. So it's 1, 1, 1. Then you have 1, 1, 1, 2. Okay, that means you have full disagreement on first name and last name, but you have agreement over between file A and file B over the year of birth, okay? And then between file A and file C and so on. The 222s would be kind of an interesting configuration in the sense that you have agreement over file A and file B, but not file C for all 3 fields, okay? And similarly for the 333 and the 5555, those are agreement on all the fields. It turns out that we observe 38 of those, okay, in this example. And we're going to maximize the likelihood using the EM algorithm. What we have is 5 independent Poisson regression. It's a latent class model with 5 latent class. That is the 5 partitions, the 5 hidden statuses define 5 latent class. And we don't know the identification of the latent class for each triple. This is what we're trying to find out. So each latent class here as 125 category. That is, each cell here is going to eventually be divided in 5 different parts through the EM algorithm. So and we have a conditional independence model here with 65 parameters with 13 parameters per class or per partition, if you will, with an intercept that ensures that the Poisson characterizes a multinomial. The latent class model has been around quite a while, and usually the goal of latent class analysis is to eventually identify the latent classes. You don't know what they are. Now, there are some applications where you don't really even need to identify the latent classes. We've seen George Schaefer presented big LC a few weeks ago, but very often, and in record linkage, we are trying to identify the latent classes. As I said here, we're going to end up with 625 estimated cells. And we're going to use the Sadinle and Fienberg classifier to decide whether they are in class 1, class 2, what the status is, whether they're 3-way matches, they're all standalone, or they're one of the pairwise matches, thereby identifying the classes in the process. Okay, so the Sadinle and Fienberg classifiers is a generalization of Fellegi-Sunter, and Binet and Stewart show that it's exactly the same thing as Fellegi-Sunter when you have only 2 classes, matchers and non-matchers. And the Sadinle and Fienberg show that they can apportion the triple among the 5 classes, or how many classes there are, depending if you're looking at pairs, triples, or quadruples, and in a way that is comprehensively optimal. Okay, but that is not necessarily what we want to do here. We're not necessarily looking for comprehensive optimality. Let me be a little more specific about this. Okay, what's happening, however, when we try to estimate that model here, is it's not estimable. And that's very often the case in latent class model. And there's a number of ways to deal with that. I'm going to talk about that, but I want to focus on the methodology that Steve Fienberg and Alessandro Rinaldo introduced in a few years before Steve passed away. That's one of the last things he did, is the extension of the classical maximum likelihood estimator to allow for collapsing dimension, essentially allowing for infinite parameter. So here, out of the 65 parameters, there are only 47 of them that are estimable. I'm going to show you what that is in a moment. And there's only 288 cells that are estimable out of the 625 cells. And what Fienberg and Rinaldo suggests is to substitute structural 0 for the unestimable cell. Essentially, they're extending exponential family to allow for infinite parameter. Okay, and anyway, see, this is what the classifier, when you do that, this is the classifier that you get. As you can, I only showed the result for 5 cells here, okay? And those are the cells that have the top posterior probability, if you will, the top classifier for partition 5, that's 3-way matches, Okay, this is only 5 of the 125 cells. As you can see, some of the cells cannot be fully classified because of the dimensional collapse. The stars there indicate structural zeros that were substituted. But what I want to do is to focus on deciding whether a triple is in partition 5 specifically, or all the others, and don't necessarily care which one of the other 4 it is part of. Okay, I want to identify, declare the triple, the 3-way triple, those that I feel reasonably confident are 3-way triples, and that's going to be the strategy. It's a takeoff, a variant, if you will, of what Sadinle and Fienberg proposed. They proposed some kind of comprehensive assignment. Okay, apportioning the triple to all 5 classes all in one swoop. I'm saying instead, just identify the 3-way triple first, and then deal with the pairs, the remaining possible candidates for there would be only pairwise later. Okay, so this is a strategy that I'm saying you can do fairly easily in R. Now, when you're doing it, starting with triple, you could start with quadruple or so on. So you know, estimate the Sadinle Fienberg classifier and identify the triple. Okay, link the triple, and then enforce one-to-one matching among the triple in order to ensure that the triples are that the 3-way match do not overlap. So you're not violating the independence assumption as I discussed. Doing this, we have some kind of optimality deciding between is this triple a 3-way match or not. Okay, that's the optimality that we get. The same type of optimality of Fellegi-Sunter, that is for fixed precision, we're maximizing the expected recall. Okay, that's what it boils down to. Then you can remove the record involved in the triple and do the pairs. And of course, when you do the pair, then you no longer have optimality, you have a conditional optimality. And let's do that, okay? Okay, here, let me show you what the well, it's already there. I don't need to cut and paste. So here's the 3 file that I constructed. The top of them anyway. They look pretty much the same, but they are not. They're slight variant, and we're going to link them. And here's the sufficient statistics. Okay, for my log linear model, my Poisson mixture or multinomial. It's the same thing that I showed you on the slides. Okay, so the next thing I want to show you is the design matrix for the Poisson regression. So you have one of them, and it's called here is because we have brown bag sessions at the Census Bureau. It's not cooperating. And so it's the brown EM matrix. But this is how it's constructed. It's very easy to do in R. Okay. And there's one of those for each latent class. Okay. Oh no, this is the whole thing. Okay, that's not what I want. Well, we can we can look at the whole thing too. Okay, we can look at the whole thing from the top. It doesn't let me go there. So these are the 5. If you look at the last 125 line here, okay, from line 501, okay, this is one of the contrast matrix. Okay, it starts at line 501. You see the intercept there, This is for class 5, okay? There's 5 of them. There's one that is in diagonal to this, and another one a little further up. And so we have this big design matrix here that I'm going to use throughout the EM algorithm. It defines 5. If I were to observe status, I would have 5 independent Poisson processes, but I do not observe status. Okay. So what I want to show you is that, okay, this is the full design matrix that I constructed. And then you can run the EM algorithm. You need a starting point, and then you have an initial M step. Okay, you do a regression, the 5 Poisson regression. The starting point is constructed strictly from the observation. I'm not cheating. I have a construct in mind. I want class 5 to be the full 3-way matches. So I constructed my starting point with that in mind. Okay, and I want class 1 to be the standalone record. So I cheated in that sense because I'm hoping that those are going to be turn out to be the latent class that I want them to be. But that's perfectly fine to do that. It's still not identifiable from the get-go. And then I do a first pass. First is maximum likelihood estimation. And then I run the EM algorithm, right? At each step, I reapportion the count. I reapportion the aggregated count, and I re-estimate. And that's all. It's just a few lines. It's very simple to do in R. I'm not going to do it here because it takes this takes a while. Okay, 625 cells, and what I want to look at is the estimate themselves, and I did it 3 different ways. Look here at epsilon. That's the tolerance of the Rafson-Newton maximization procedure. Okay, in this case, it's 10 to the minus 8. Okay, that's a fairly stringent tolerance, but I did it 3 different ways: 10 to the minus 4, 10 to the minus 8, and 10 to the minus 12. And so I can show you the estimate. The count is of the count of the 625 cell involved in the classification. And here they are. Now let's go to the top. That let me go to the top. Okay, so the first one is class 1, which is I designed my starting points at that class 1 would be the standalone. So this is the estimate, the triple in class 1 that are standalone. Okay, so those in means that they point to 3 different individuals, and in addition, the first one, there's 125 of them in class 1. The first one exhibits full disagreement on all the field. Okay, and then you have agreement on birth year only, and then agreement on last name only. You have agreement on birth year in between file A and file B, but not file C, and disagreement on full disagreement on all the other fields. Okay, and so on until cell 125, where you have full agreement between the tree records. Okay, but we're still in class 1, so the estimated number of those is pretty small. It's not even an integer, right? The point here is that under the 3 tolerances, I get estimate. this is estimable. These cells are estimable. But as soon as I get in class 2, I get into trouble. You can see that these cells are no longer estimable. I become more severe on the tolerance, and it gets closer and closer to 0. Okay, so there's only 388 cells that are estimable. Let's go at the bottom. That's class 5, so those are the three-way matches. And there's only 8 of them, 8 cells among the three-way matches in class 5 that are estimable, including the very last one, which is the number of three-way matches that agree on everything. Okay, it's 37 point something, which is pretty close to the 38 in the table that I showed you before. So what I'm going to do now is compute the EMLE. But at first, I want to show you how do you find out how many degrees of freedom have survived. Okay, well, it depends on the fascia. Okay, and you can compute the fascia, the fascia, right, in English, and so that's a subspace of the column space of the design matrix that correspond to the estimable cell. So let's do it for class 5. Okay, in class 5, there's only 8 cells that survive. And these are the row in the design matrix that are associated to these 8 cells. And so how many parameters survive in class 5? Well, not necessarily 8, right? It's 8 cells survive. To know how many degrees of freedom survive, I can look at the rank of the fascia. And I have a rank function here from the pragma. Okay, there's only 5 degrees of freedom that survive from the in class 5. There were 13 degrees of freedom originally. Okay, but in the EMLE, there's only 5 degrees of freedom, and I can compute. Oh. Actually compute the EMLE. Okay, if this lets me do it. No. Okay, let's try again. Okay, so this is what the MLE look like. Okay, see zeros everywhere where the cells, when the cells are not estimable. Okay, and then I can next what I can do is compute the classifier, and I showed you that. Let's see here. This is giving me trouble.
Hey, Yves.
Yeah. Here's the classifier. Okay. So what do we have here? And I'm interested in class 5 only, in the triple. Okay. So it's 0 in most of the places. And I've ordered them by order of magnitude. So cell 125 is the most likely to be a triple. Okay. And then what I can do is use the classifier to classify the triple. Okay, and here they are. Oh. Okay, here are the triple. But there are, if you see here, there's a detour often comes more than one time. So I have to enforce 1-to-1-to-1. Okay, that to ensure transitivity, to make sure that the assumptions are verified. And I can use a greedy algorithm to do that. Okay. So, but these are the nominal triple. And then I can have the final triple. There's 55 of them. Okay, Wendy, should I do something now?
Yeah. Is it time for questions?
Yeah, I think we can look at question. Let's see here.
Oh, can you put that back up, what you just had?
Okay, let's put the thing back then. Oh no, I want the whole screen.
Yeah,
But I
perfect.
want the chat. Let's see here.
Oh,
Show
yeah,
chat.
there's no questions in the
Okay,
chat.
so okay, so it's a verbal question.
Yeah, it's actually my question.
Okay, go ahead.
So the last column there, is that the probability that
Yes,
it's a match? Am I saying that right?
exactly. Let's go back. It's not too far. So I only put class 5 there, but there's a probability of being in class 1, class 2, class 3, class 5. Okay. And but I'm only interested in class 5. So it's 0 most of the time. Okay. For just about all the cells. There's only 8 cells for which the probability of being in class 5 is not 0. And it's these 8 cells there because there's so many parameters that are not estimable. Okay. So cell 125, that's observed agreement on all the field, and among all, full agreement on all the field between the tree record. File 535, that would be full agreement between first name, between the tree record, but only pairwise agreement between file A and file C on last name, and full agreement between the tree record on year of birth. That's 535. So that has a probability, a little lower probability. It's a posterior probability, if you will, which is a little lower than 555. So it's 64%. So Fellegi-Sunter type decision, and that's a very good question. So you are going to set a cutoff. Okay. Now, when you look at the pair themselves, like I showed you, that gives you a better idea how to do the cutoff. You see how here they're ordered by those probability from the top down. Okay. And so you get to determine where your cutoff is. Basically, after you rank it in decreasing orders. That's how you do the classification. But in the first bunch here, there are repetition, and that's not allowed. And also, I'm going to put my cutoff here just above the last two. Here, these are the top 5. I'm going to put the cutoff just above the last 2. Okay, the last 2, they disagree. Let's see here. I think that's see, I don't remember. Let's see. That's the 5th one. The fifth one, that's 523. Okay. So those are 523s, whatever they are. They agree perfectly on first name, but there are problems with either the last name. Here the last name looks fine, right? So, so what's the issue here?
It looks like the year is different.
Those are the clean ones. Here are the corrupted one. So I got rid of I get rid of the 0.016 there. So those are pretty bad, right? They agree perfectly on first name, but there are a problem with both the last name and the year of birth. Okay, so I got rid of those. I cleaned up the nominal triples, and I applied the greedy algorithm. And so those those are the triple that decide are triples. Okay, that answer your question.
Yeah, okay. Thanks, Yves. I have another question. So so I don't think FastLink or Splink do they do triples?
No, it doesn't do triple. So
Okay.
that's the point. You have to do it does two classes, okay, pairwise. And that's what I'm gonna do next. And do we have time left? Yeah, that's what I'm gonna do next here.
Well,
And
okay. Well, while you're doing that, let me so if you did do, say, FastLink and you were wanting to do the three files, I guess you could check A versus B, and then I mean you
that's
could check
right.
all
You
of them
can do
pairwise.
A versus B and A versus C and B versus C.
Yeah.
But that's not you cannot assert triples by doing that. Okay,
Yeah,
so
exactly.
you do that, you get 8 parameter in each case. You would have 24 parameters, so you have a much
Yeah.
less discrimination power. Okay, here we initially we had 65 parameters. We lost a bunch of them. We're down to 47, but it's still much better than doing only pairwise. But what I'm going to do next is I pull out the records that are involved in the triple, and I'm going to match the remaining all the eligible pairs after pulling out the triple, and I'm doing my own EM algorithm, but FastLink can do that. Once I pulled out the triple, I can throw in all the pairs together and run FastLink. Okay, but I'm going to do it myself. I guess hopefully not because I'm an egomaniac, but just for the sake of the argument. And that goes pretty fast, actually. You can run the EM algorithm, and I'm doing it 2,000 times. And that's what FastLink does. It runs the EM algorithm. You can see here, it's only 2 classes that get reapportioned at each step. Each step reapportion the counts between the pairs. Okay, for each pair, it decides how many are matches, how many are non-matches. And FastLink does that really, really well, okay? But you cannot extrapolate directly from that to decide whether something is a triple or not, because the pairs in the triple are not independent. Fellegi-Sunter, the classification of the pair based on Fellegi-Sunter assumes independence between the pairs. It's a multinomial distribution of independent multinomial trial. Okay, and so this takes a little bit to run, but thank you for this question. That's really the heart of it. Okay, and so you have 5 classes with your EM algorithm if you want to do triple. If you have quadruple, I think it goes to 24 classes, latent classes. And Sadinle and Fienberg tried to assign the triple and the pairs simultaneously. What I'm saying instead is do it this way by stage. First, identify the triple, and then remove those records from the tree files, and then run the regular pairwise Fellegi-Sunter method to identify the double, to identify the pairs that are going to be only involving, well, obviously all the pairs that are subsets of the triples are matched pair also, but you've already accounted for those. Okay, you remove the triples, you remove the record to find the other pairs, and then you know you only have disjoint pairs. They're not going to overlap. Okay. And so at the end, you know that the assumptions are being respected if you go that way. Does that make any sense? So that's the issue. So I did ask the question to Ted last time, and he says that he was working on something to do triples and to do higher order cluster. One of my questions when he presented last time. He's working on that. I think he's working with Rebecca actually on that. And they're using a Bayesian methodology. I have nothing against Bayesian, but I'm saying you can do it using traditional methodology, maximum likelihood estimation, using the theory of Steve Fienberg. And here's a classification for the pairs. I have not run the EM algorithm yet, okay? There's only 8 possible choices for the pair, right? 8 is agreement on all 3 fields for 2 records, and 1 is disagreement on all 3 fields for the 2 records. And this is all the pairs that you've got left. So you pick up an additional 99 pairs here, depending where you set your cutoff. This is as far as I got, okay? And this is still work in progress. And what I want to do now is go back to my.
Hey, Yves, I'm sorry, I had to jump off for a second. Did you see that there's a question in the chat?
Oh, there is one.
Yeah.
Okay. So let's see here. How can I
So he said, I'll read it to you. He said, are we still on agreement disagreement paradigm, or can we use
yes. But for the triple, there's 5 possibility. It's still agreement disagreement. But the triple, there's 5 possibility, right? There's full agreement between 3 records, agreement only between A and B, agreement only between A and C, agreement only between A and C, and only between B and C, and full disagreement. Okay, but it's still agreement disagreement. We're not considering the content of the field. Okay, so let's see. So we can use probability match age with.
Yeah, so maybe I think both things maybe are the case, because you could oh, okay, so I think maybe like if you would be saying agreement disagreement on, say, on year, but you could do like agreement disagreement and then like a maybe.
Yes, like here, agreement is disagree on all 3. Okay. Here, you have disagree, all 3 records disagree on first name, all 3 records disagree on last name, but the records from file A and file B agree on year of birth, but
Okay,
not the record of file C, and you have 84,000 of those.
yeah, but I think that's still agreement disagreement on,
It's
say,
still agreement disagreement, but there's
yeah,
5 possible configurations.
yeah,
Okay, because you have 3 records. So you can have full disagreement, you can have full agreement, but you have something in between, only pairwise agreement between 2, and the third the record not agreeing when you have 3 records. But it's still agreement disagreement.
yeah. Okay, hopefully that answered your question, Richard.
That's the best I can do. It's let's see here. Okay, these are the well, what is this? Oh,
You could go ahead and go back to the end where you were doing
Here are
the
the 5 partitions.
huh.
Full disagreement, agreement only between A and B, agreement only between A and C, agreement between B and C, full agreement. Okay.
But no partial agreements.
No partial agreement between fields.
Yeah, exactly. That's what I was trying to get at.
Partial agreement within the triple.
Yeah,
It's not the same thing.
yeah.
Okay. Yeah. Thank you for clarifying that. We're still, it's the comparison between the first name is still yes or no. Okay. It's only yes or no each time. But because you have 3 records, there's 5 possible partitions.
Hey, Yves, I think you maybe this is at the end, but I think you are you mentioned some journal article or some articles. Do you have references to those at the end? Oh yeah, here's one, the
Yeah,
Fienberg.
I would be happy to uh, 2 main papers here. Okay, that I've been
Okay.
drawing, and the Fellegi-Sunter 1969 paper. So those are 2 landmarks, very important. They're both JASA papers. Okay, and
Oh, Jazza? Okay.
okay, those, yeah, please, I could give you the full reference, but those are the years, and they're both JASA. They're both the Journal of the American Statistical Association. If you look that year, you should find that without any trouble. I'm sorry, I did not put the.
That's okay. It you got the title and the authors and the year.
Okay.
So well, that was super interesting.
I'm going to stop sharing now. Thank you, all 6 of you, whoever you are.
Well, there's some people we recognize. They're here. So thank you so much, Yves. This was super interesting. And yeah, I'm still learning about record linkage all the time.
The fast link is terrific, by the way, but that's the limitation. And we have all sort of ways to compensate for. And if Fellegi-Sunter, they say you have to do a clerical review to resolve the inconsistency. That's how they got out of the problem, right? Well, good luck if you're going to do it on a massive scale, record linkage, to do your clerical review. And so that's the issue here.
No, I think this is very interesting, and I love how you've shown how to do it in R. And not only that, you showed not in R Studio, but what I call R GUI
I'm
or
not good
something,
at
right?
that. I'm sorry. Yeah, it's just too good for me, R Studio.
Yeah, no,
I'm too old.
No, hey, Yves, I used that interface for a long, long time. I had to force myself to use RStudio, and it wasn't all that long ago that I learned RStudio. So I'm right there with you. But I just wanted to point that out to people. All right. Well, thank you again, Yves, so much.
Okay.
We will.
Have a nice
If you send me
weekend.
your code and your slides, then that would be super helpful.
I'd be happy. Okay. I'm sorry. I should have put my email address. Okay, it's
Well,
Eve.
people could email me.
Okay, I'll be happy.
Oh, good. Richard put something else in the chat here.
Okay, what is it? What is it here?
He said, I talk about linkage in a lecture of my university data collection methods course, as it is important. No, you're right, Richard.
We will.
Record linkage is such a fundamental task in so many things that we do with I'm going to say a big data, right? That
the people
yeah.
in my first slide, you should feel free to contact them also, the researchers. There are plenty of researchers, plenty of other places too, okay? But I can only mention those at the Census Bureau.
Yeah, thank you. And most folks should know us, but Yep, my email is wendy.l.martinez@census.gov. So just let me know, and I am going to try to get the slides and things from these seminars posted if I can figure out how to do that and get the time to do it, so that things will be kind of connected and you'll have them. So yeah, so Yves, if you and I will work to, you could give me the stuff later.
Yes. I'll send you the slides.
Great. And the code.
Okay. Thank you very much.
You're welcome. Thank you. And thanks, Richard, for being here, and our other attendees too. Thank you again. And keep an eye out for the July meeting. And next week is GASP, Government Advances in Statistical Programming. Lots of fantastic talks. Again, give me an email, send me an email if you need to know how to register, or you can probably Google it and find out too. All right, great. Thanks, everybody. Thank you again, Yves. And Richard, again, good to see you.